Hey, it's me, Steve, and it is another episode of the Geo-Files. I said I wasn't going to do another one this year. I lied. This one's going to be on correlation, since I brought that up in my most recent Geo rant. But I'm just going to explain to you how geologists correlate strata. I'm going to use the board here to do most of that. Because correlation is really key, but I might as well just, I gave a detailed definition of what it was in GeoRant 71, which was the most recent, but I've kind of simplified it a little bit since then. Basically, correlation, when it comes to geology, is the practice of fitting different geologic strata together over distances. Now, a distance can be short, it can be huge, but they're separate, physically, either by geographically separated by large distances, or geographically separated by like a river valley or something like that. But it's important to establish these things because it determines that it establishes age relationships between rocks, both absolute and relative, which I'm going to get into. And well, we use that to decipher the history of the planet, and that's important. Because knowing how geologic events occurred in the past, it's key to the future. We can understand future processes as well as present ones a lot better if we understand just how rocks relate to one another in actual space and time. But that's it for the intro. Let's get started. Hey, all right. So, like I said, we have absolute and relative time that we can use to correlate rocks in a set of basic framework. And here are basically what the principles and laws we work off of in order to begin the correlation process. So these first four, I am gonna go into them one by one here in a minute. But you have the law of superposition, principle of lateral continuity, principle of original horizontality, and principle of cross-cutting relationships, and unconformities. Now these first four here, I need to look for a second to actually remember how to spell his name. He's a Danish guy, or was. This is Nicholas Steno. He's the one that came up with these concepts. In the late 1660s, he was a Catholic bishop later in his life, but he developed these four principles, which we still use today. Unconformities, Steno didn't know about unconformities. People after him kind of did, but didn't really think about it much. It wasn't until James Hutton, who's often considered the father of modern geology, and he was English. He was the first to identify and describe unconformities. There's a couple famous places, Jedburgh and Siccar Point, and I believe he defined unconformities in those areas. I believe it was 1780s. So, but we use those as well in order to correlate units over distances. So I'm going to take each of these concepts one at a time right now. Now you got to remember, when we were originally trying to figure out geologic history in the 17th, 18th, and 19th, even early 20th centuries, we did not have radiometric dating. I'm going to come back to that later. But so all we could tell were how rocks looked at one another in space and time. And I'm going to talk about the law of superposition first here. The law of superposition just basically states that older rock units are originally deposited on the bottom. So if this would be a cross section, And younger ones are above. Say this is a sandstone, this is a shale, this is a limestone. So what that basically says, in a normal sequence of undeformed rocks, the oldest will be on the bottom and the youngest will be on the top. So here, the sandstone was deposited before the shale was deposited before the limestone. All right, now I'm going to talk about the principle of lateral continuity. And I just drew this quick diagram. This is a cross section. This would be a river valley. We'll just say this is my little river in the bottom here. We'll just say he's flowing that way. And this is a V-shaped valley. I know this is not exactly to scale. These distances are here for a reason, though. 300 meters this way, 100 this way. The reason why I gave distances here on this valley is because the principle of lateral continuity says over short distances, like a few hundred meters, you can correlate units just across something like a valley or a dome structure, or say there's a big lake in here or something, blocking one side for another, or a small lake actually, that you can just draw things across in order to correlate them, even if they are lacking in fossils or anything like that, or something you can absolutely date. But here, you can kind of see, and I put a fault in here, right? Because a fault is technically a type of unconformity. And this is a reverse fault because we had this move up. So I just want to add a little complication to it here for you. But this basal unit here is our igneous. We'll just say it's a granite. That's why those lines are there. These with the dots are sandstones. This brick-looking stuff in cross-section here is limestone. These dashed lines indicate shale, and this black unit is just a lava unit within the shale. Now, what we can do here is we can connect these units. Like, we definitely can see the granites correlate, the sandstones, and the limestones, but we have a fault in here, which I'm going to extend up. So, and we can correlate this limestone and this limestone here. But my question to you is this limestone correlative with this one? Well, according to the law of lateral continuity, it is. We can see we have a sandstone at the base of each limestone here, and we have this granite. And above it we have a shale, and over here we have a shale, even though the shale here has been eroded. So this limestone, even though there's a fault here, we'll just bring it to the fault, is continuous to this limestone. And then we have our shale here, and our shale here has a lava unit in it. And our lava unit, if we extend it to the fault and relying on the topography of the underlying units, might look something like that. I'm just drawing this on the board so I know it's not perfect, but we have a vague anticline here along with a fault. And that lava unit is going to correlate with this lava unit somewhere over here if we extend our fault up. The lava unit is within the shale, and the fact that it pinches out doesn't mean anything over this type of short distance. So first, we have our granite. So this would be, I'm not going to give formation names, I'm going to just give them numbers so I can, because it's easier than trying to name stuff here. So our granite would be unit 1, this would be unit 2. Everything that's has the same numerical number is correlative. Our limestone would be 3. Our shale, both above, well, I guess not technically above, would be 4. Our lava would be 5, and the shale above the lava would be 6. All right, so that's the principle of lateral continuity, essentially, in a nutshell for you. So let's move on to the next one. Okay, the law of original horizontality basically just states that on the Earth's surface, rocks are deposited in flat lying units. And there are exceptions to this, like a deposit next to a cliff face obviously isn't going to be flat lying. It will have what we call initial dip. And over long distances, everything has some sort of initial dip. Because if a sediment is being deposited in a basin, Obviously, the basin's bottom is going to go like this over long distances, but on a small regional or local scale, it's going to be deposited essentially flat. So all sedimentary units and even igneous units deposited on the surface will have this flat lying appearance when they're originally deposited before they're deformed. All right, but I mean, there are obviously exceptions to this, but just say that this is a cross section of a sandstone unit. We'll say this is all basically one type of sandstone, and these will be bedding planes. You can get things like trough cross bedding in it. You can get planar cross bedding in it that might go this way in one direction and may go this way in the opposite direction up top, but the unit itself is still horizontal over any significant distance. Cross beds usually don't continue very far. They're usually very on the structure, at least especially marine cross beds, they're like on the structure of the human scale. Like, you can pretty much delineate these and they don't go very far, or they'll turn, or they'll do something like this and eventually become flat lying just over further distances. Okay, now I'm going to talk about the principle of cross-cutting relationships, and I'm also going to use the same diagram to talk about unconformities, and that'll wrap up the introduction here into how we perceive things in a field. This will just be a generic cross-section I just made up. This is your granites. The little circly pebbly things are conglomerate, the dots are sandstone, the dashed lines are shale, the brick stuff is limestone, just as before, and these two things are igneous intrusions with the squiggly line and the thick black line. Okay, now the laws of cross-cutting relationships, basically what it tells us is if something cross-cuts in an igneous type regime, with sedimentary here in this case, something cross-cutting something else is younger. So the fact that this is inside this granite tells us this intrusion is younger than the granite. It has to be. You can't intrude something that doesn't physically exist. All right? So that's just basic logic. If it's not there, you can't screw with it if it doesn't exist. But that's basically what the law of cross-cutting relationships is. And I'm going to show you how that combined with unconformities can give us a sense of relative time. And I keep talking about relative time here because what I'm doing here is I can tell you what came first, what came second, third, fourth, etc. But I have no clue how old any of this stuff is. I can't date it, all right? And unless somebody does that, it's just this geologic unit is older than this one, and that one's older than this one relative to something else. That's why it's called relative time. Now, and that's the problem early geologists had, and that's why our geologic time scale is broken down the way it presently is at present time, is because a lot of these names like Cambrian, Ordovician, Silurian, Devonian, Carboniferous, all of these, and Precambrian, all of these come in roots from, they could tell Cambrian type sediments were older than Ordovician, and that Ordovician was older than Silurian, but they couldn't tell you how old that stuff was. It wasn't until radiometric dating that we were able to start doing that. And of course you can use fossils to correlate things too, which I'll get in a little bit. But basically using this looks really complicated, but it's not. I have another fault right here. It's kind of sloppy, but that's what this curve is, a thrust, so this is thrusted up. And using what I just showed you, what can we tell from this? All right, well, it's really easy to say that this granite is the oldest. It's the most highly deformed. We got two igneous intrusions and a fault offsetting it. All right, so this is the oldest, and using the law of superposition, although it doesn't always apply to igneous intrusive bodies, we can tell that this is our oldest unit. So unit 1 is our oldest. And from that we can gather this, our conglomerate, is also younger than the igneous unit, and there's several lines of evidence we can use for this. Number one, it's on top, original horizontality here. It's made, we'll say these pebbles have a lot of granite in them, so it was derived from the granite. And we have faulting and cross-cutting relationships through it, just like we did with the granite. We have two igneous intrusions of fault throwing it off. So via that, we can determine our sandstone is younger than our conglomerate. That's a little bit of it right there, right there. So our shale, that would make our shale, even though, that would make our shale younger than the sandstone for the same reasons, for the same reasons why 3 is younger than 2 and 2 is younger than 1, 4. So we had the shale. So first we had our granite, and I'm not going to talk about nonconformities yet, but if we had our granite, our conglomerate, our sandstone, then our shale was deposited. Well, what happened next? Well, this fault offsets this igneous intrusion. Okay, so we know that igneous intrusion happened before that fault. You can't fault something that isn't there. Okay, so our igneous intrusion would be unit 5, even though it cross-cuts all these other units. All right, and that would make, and since this, this here, notice our fault stops right here. Okay, I'm going to get that in more detail in a little bit. But since our fault stops right there, it doesn't go into this, we know our fault, it's not an actual geologic unit, but it's an event, but I'm still going to label it number 6. It's another reason why I'm using numbers and not names. So that happened after the deposition of this. We don't know how long that time frame is. We can just tell from field relationships that's what happened. All right. Now, we have this igneous intrusion, and this intrudes everything, cuts straight up, just through it all right? So, the fact that this intrudes this tells us this dike is younger than this limestone. So this limestone has to be unit 7, okay? And that would just leave our dike as unit 8. All right. Now, before I start summing all this up and putting this into a bigger picture for you and trying to organize it, I'm going to sit here and talk about unconformities because I kind of need to in order to explain some things here. Like, how do we get this limestone crossing the sandstone, not only the shale, but the sandstone, the conglomerate, and the granite? Well, unconformities. Unconformities, you have, I'm going to write them down. I'll write them down. You have 3 basic types. You have a non-conformity. You have, can you guys see that? Yeah. You have a non-conformity. You have angular. I'm not going to write down conformity. But you have non-conformity, angular, unconformity, and you have a what's called discontinuity. All right, and they should all be represented here in this. I believe they are. I may have to actually, no, they are here. I'm going to have to add a unit. Actually, I won't. I'll just do this, and we'll say that's a symbol. It's not fossil. That's hard ground on top of this bed, and I'm going to use that to talk about discontinuity. That looks too much like a G. Discontinuity. Okay, so, all right. Now, a nonconformity. Nonconformities are basically unconformities that exist between the relationship of igneous or metamorphic rock and sedimentary rock. We have that here. We have the dikes, we have the granite, and we have this. So there is an unconformity here on top of the granite and our overlying conglomerate. Okay, and the reason for that is you have 2 different types of sedimentary, or 2 different types of rock. You have igneous and sedimentary, and those have 2 totally different type of origins. But in this case, that contact is erosional, but it doesn't have to be. Say this was all sandstone and this igneous body intruded into it, this granite intruded into it, that would still be a nonconformity, all right? But it wouldn't be an erosional one, all right? Erosional unconformities are just something we say that can fit all three of these. It's just, usually we like to say an erosional unconformity to, sit there and let people know that erosion has occurred. Now your angular unconformity, basically that's where you do not have, remember I said the law of original horizontality is stuff at the surface likes to be deposited in flat beds. Rocks also like to be deformed, and they can be tilted and uplifted. We see this all the time. I mean, I've got dozens of pictures of that just in my other videos and stuff like that. But you'll get rock units that'll become lifted, tilted, and then they'll start to get eroded, and something else gets deposited on top of that later and forms an angular unconformity. That's what this is. You have your dipping beds going this way here, but your limestone dips that way. This is your angular unconformity right here, and it's also erosional in this case as well. All right, then you have your discontinuities. Discontinuities are just breaks in sedimentary environment, essentially, where non-deposition has occurred. Sometimes erosion can occur. You can have erosional ones, but you don't have to. Like what we call a diastem is an example of that, and that's why I put these squiggly lines here. Say this limestone, these two bottom beds were deposited, and then deposition for some reason just stopped for a small period of time. Maybe 100 years, maybe 10,000 years. Well, what starts to happen on top of that limestone is that it would become subaerially exposed. So even though it would be underwater, it's still going to be exposed to sunlight and mineralization. So you'll start to see things like pits in it, and it'll be distinctly like red. It'll be limonite there. But then once that's done, it goes right back to being deposited just like all the rest of the limestone. So I think that's all I want to say about that. Now, how does this all tie into relative time? All right, so like I said, relative time, you cannot determine actual dated relationships. That's not the point of it. But relative time, even from this cluster, we can confidently say at time, unit 1 here was deposited, and it may have had a ton of sediments or something else on top of it before it's all been eroded, but that was deposited. Then it was eroded. Then our conglomerate was deposited on top of that, followed by a sandstone, followed by a shale. Now at that point, something happened, sedimentation stopped, we had an igneous intrusion here come through. Once that happened, at some point of missing time between that and our next sedimentary unit, we get a fault. The stuff was faulted, all right? And erosion obviously had occurred between units 2, 3, 4, and 7 here. So by the time 7 started to be deposited, we already had an angular unconformity. So we know there's missing time between what happened with the fault and the deposition of unit 7. All right, we don't know how much, but we know there is missing time. And then finally, unit 8, this igneous intrusion came in and cross-cut everything. So we know that was the most recent event. So all we can say for sure is that Unit 1 is really old. 2, 3, and 4 are old, all right? 5, to include the fault, which is not a geologic unit. 6 is middle-aged here, relative to everything else. 7 and 8 are the youngest, all right? And we can use those things, and originally this would be the type of thing people would use. Okay, so we would take this interpretation from the field, and in the early days, we would sit there and say, okay, try to form a picture, So we would sit there and say, okay, my unit 1 would be I did it again, would be my primary geologic period, all right, just because it's the oldest initial primary, and this is actually what kind of occurred. And then my units 2 through 4 would be my secondary. My secondary units. Unit 5 could either be secondary or not, so I'm just going to write the number. Like I said, 6 is not a geologic unit, it's a geologic event, so it's not included. And my number 7 is tertiary. And we'll just say my number 8, since it's the most recent I have, would be my quaternary. So, quaternary. Now, this is kind of how it originally happened. So they would just group these, how they related to one another in the field over distances. And like I said, 5 is just, and it could be either be secondary or tertiary in this kind of situation. But we have our primary, secondary, tertiary, and quaternary now. So we're starting to develop geologic periods, a geologic column here. Now that is actually what occurred, not this specific example, but that is what occurred. And the primary would eventually become Precambrian, secondary would eventually become what we refer to as the Paleozoic and Mesozoic. Tertiary was tertiary up until 5 years ago when that term was dropped. We still use quaternary, all right? They had no idea the vast times, like quaternary, it was extensive on the surface, quaternary deposits in Europe and North America, but it only represents 2.4 million years, as where what they call primary is 88% of the Earth's history, from the formation of the Earth at 4.5 billion years ago to 541 million years ago. But like I said, they had no way of knowing that at the time. Okay, I'm going to touch on, and I'll wrap up relative dating here and then get into absolute dating. I'm going to talk, so here we're still in relative time, and I'll get into absolute time in a minute. Fossils. We can use fossils to correlate units, but you can still have fossils that might appear in a shale and might appear in a limestone over a great distance that have very narrow band of time. So we know those are age correlative, they are the same age, although that shale and that limestone don't have to be given the same geologic name, because like I've said before, we do not use fossils to define lithostratigraphic units and formations. All right, but the continents, those guys, oh man, I should have looked this up ahead of time. They have teeth fossil, jaws, and if I remember correctly, they are basically worms with teeth. All right, they are very species specific. Like their teeth are very definite. That you can pick these out, pretty defined. They are usually isolated to a very narrow span of time. So now, even though you're using relative time, you can sit there and use fossils to kind of correlate things a bit more accurately, like, you know, say over great distances. I don't want to do that. Say this is more of a distance of 1,000 kilometers. So we have different units, and you know, that kind of separation, you're going to have all kinds of intrusions, faults, and things like that. But we'll just say here we have a sandstone. Here we have a shale. Here we have a limestone. And here's our sandstone here. Here's our shale here. Oh no, we won't make this a shale. We'll make this a limestone. Alright, this will just be igneous here. And we'll know that there's igneous over here too. And so we have limestone here, and then just say we have shale here. Now it kind of looks like a geologic dilemma here, because you have no problem with these igneous layers, you have no problem with the sandstone layers, but then you have shale under your limestone. Here you have no shale under it, but you have it above it. Obviously these are different formations, and they would likely all have different formational names over that distance, and that's fine. But say the sandstone has continent X at the top. This limestone has continent Y at its base, and only at its base, okay? And then this shale throughout it all right, has continent Z throughout it, okay? Now, you come over here and you find continent Y is here. But in the shale, there aren't any, all right? So you don't have here, but here you see you have Z. So what that tells us is that, barring geologic structures in between the two, that these sandstones correlate, this shale pinches out, and this limestone dominates. So what happens is, and then you would likely have shale over here as well, or something else. So this is your unit 1, sandstone's your unit 2. Let's just say this is your unit 3, this is your unit 4. Because in reality, geologic units over these kind of distances thin and thicken over very long distances. So this is not an uncommon situation. So, but using continents, you can get a more detailed picture of this sedimentary platform in which these things were deposited, and a better understanding of relative time. Because now, even though over great distances, here you have 1, 2, 3, and 4, here you have 1, 2, 4, and 5, and this may, in between here, you may not recognize an unconformity, and there may not be one. Unconformities do not continue forever. Conformities do not continue forever. So 2 and 4 may not even have an recognizable unconformity between the two. So what this tells us is that 1 is on its own, 2 is on its own, but the bottoms of units 3 and the bottom of unit 4 were deposited at the same time, even though they are distinctly different lithologic units. Okay, now we're going to talk about absolute time and radiometric dating. Now, I'm only going to touch on this because this is a whole division of science that can be spent days talking about. I'm just going to touch on it because we use radiometric dating to determine absolute age, and there are 3 main types that are used in geology, all right, and archaeology. Well, this one for archaeology, and that one as well, and paleontology, all the other ones, all right. So one most people are familiar with is carbon-14. Carbon-14s will decay into carbon-12 when something dies. This is, in black here, is the type of radiometric dating. In red here is the half-life, all right? And in green is when the time frame in which this dating is accurate. Carbon-14 has a half-life of 5,730 years, all right? It's not very long, especially in geologic time. It's real good for dating recently dead things and things like glacial deposits, modern quaternary ones. But it's only good for about 200 to 50,000 years before present. And we use carbon-14, and when you hear radiometric years before present, 1950 is the baseline, and it's based off carbon-14. Because even on a short scale like this, 1950 would be the present, and it's 2017, so even in that 67 years, 67 is nothing compared to this number. So, but that's just a little side rant. So basically, if something's 200 to 50,000 years old, you can date it using carbon-14, assuming it has an organic origin. All right, you can't pull carbon-14 dating from a granite. Right? You can't do it from a lava or a sandstone or anything like that. All right, it just won't work unless there's an organic component. Another one we commonly use derived from zircons is uranium lead. And this one is very common. Zircons are a very reliable mineral, and they don't weather very easily, so they're really good for dating things. It's hard to deform them, although under metamorphic conditions, dates will get reset. We are aware of that. But the half-life is about 710 million years. So that means if you have a chunk of uranium that was originated during the beginning of the Phanerozoic, it hasn't even hit its half-life yet. But that's good from about 1 million years to the beginning of the age of the Earth, 4.5 billion. And this, we've got really good
dates. I mean, we're talking, we margin the errors of 0.1 to 1% maximum. I mean, you start dating things 1 billion years old and you might be off by 2 million years, which at 1 billion years isn't anything. You also have potassium argon dating. Now, this one I'm not very familiar with, so I'm just going to, I mean, I know what it is, but I'm just going to spout out what I know. I have approximately 1.25 to 1.26 billion years half-life, and the reason why I have that is because apparently potassium has 3 typical isotopes that will decay into either argon or calcium, so that's why there's a range there. And basically it's good from about 10,000 years before present to the age of the universe, if you could find a chunk of potassium that's that old. But obviously on Earth is, you know, less than half the age of the universe. So, you know, yeah, but theoretically you could. So that's all I want to say about radiometric dating. If you want to find more out about it, just do a search. There's plenty of papers and stuff that explain the process in real good detail. Okay, now I want to explain how absolute time can be used to correlate chronologically units, because remember we have chronostratigraphy and basically lithostratigraphy in a nutshell. Obviously it's more detailed now. I did a whole Geo-Files episode, the last one, on lithostratigraphy, but for the time being I'm just going to simplify it to those 2 things. And this is loosely based on a real world scenario. When I wrote my Copper Harbor paper, which I need to finalize and resubmit now that the changes have been made. And this is a problem that I had with one of the guys that originally suggested my paper get rejected. He was a geophysicist. He understood paleomagnetism very well, but he was not a stratigrapher, and I don't think he understood the difference between chronostratigraphy and lithostratigraphy, even though the title of my damn paper is lithostratigraphic. But the 2 are not the same, all right? Now that we have absolute time dating and we can date things, all right, we'll just say, you know, this is a, you know, granite, the B is basalt, the A is andesite, the R is rhyolite, all right? And then we have our conglomerates over here, and we have some shales here, some sandstones here, which we do not have on this side, all right? And we'll say this is 300 kilometers and say this is a big body of water, like, I don't know, Lake Superior. So we have a blank zone in our knowledge here, all right? Now we can get aromatic maps and gravity maps, and we might be able to pick out things like faults and stuff like that, but actually we have no physical data. There is no rock in our hands to sit there and tell us what is actually physically there. We can make our best guess, but until somebody drills down, we really don't know. And what's the point of doing this? All right, so here's our basalt here. We have a basalt here. Okay, say this basalt is dated at 1.9 billion years. All right, say this one is 1.18 billion years. All right, this basalt is 1.10 billion. This rhyolite is 1.10 billion. All right. Now this andesite, we get 1.09 for the andesite here. But in this andesite, we get 1.08. All right, these are hypothetical, like I said, this is loosely based off a real example. All right, we have one more basalt in here, which we get 1.064. And because we can't directly date the conglomerate, all right, but then we have an igneous intrusion in the middle of it. But this conglomerate here is 1.07 billion years, all right? And this basalt is 1.05, and then we'll just say this one is 1.04, all right? So we have these absolute ages now. All right. So we can tell that this basalt was deposited before this one. The rhyolite and this basalt were deposited at the same time. These 2 chronostratigraphically correlate. They do not lithostratigraphically correlate. Well, they're not the same geologic unit. Why? All right. Number one, we got 300 kilometer separation of distance here. And there's things like faults and synclines and other stuff in here and who knows what else. But one is a basalt and one is a rhyolite. Those are two totally different rock types. They're both very extensive on their side of the lake, but they are not lithologically the same unit. They are the same chronostratigraphic unit, but not the same lithologic unit. All right, and that's important to understand, and that's something geologists don't even understand a lot of times. All right, and then we have 1.08 here, or 1.09 here. So this lava unit is older than this one. We have 1.08. This andesite. Oh yeah, these two andesites. See these two here? They're both andesites, stratigraphically above the basalt and the rhyolite. They both yield different ages. Do they correlate chronostratigraphically? No, they do not. Lithostratigraphically, do they? Sure, if you can prove it. Like I said, there's this big blank area, so it's better just naming them different things. One is younger than the other, but in lithostratigraphy, we don't care about age. Lithostratigraphic units are age independent. So then we get the I screwed up here. I put a date on the conglomerate, my bad. We can't date the conglomerate because you can't date sedimentary rocks. Well, you can't absolutely date them. But we have a basalt here that's 1.06 in this much thicker conglomerate. And here we have a basalt that's 1.05, and we have one that's 1.04. So it is possible that these two conglomerates correlate, at least the basal parts do. But we don't know that for sure, so we should just leave them different stratigraphic units. But now that we have absolute dates for this stuff, now notice the shale and the sandstone does not, but the igneous intrusions have stopped, or the igneous lava flows have stopped at this point, so we have to use other methods to date those. But we can get a time frame pretty good, and say this granite right here is dated at we'll just make some room, is 1.23. So we know that this sandstone didn't have a lot of time to be deposited. So we know there's an unconformity here. We know there's one here. But unconformity is another thing too. What's your scale? Technically, every separating unit here has an unconformity. But if you're pulling out, zooming out, you can still lump all of these into one unit and just not mind about the unconformity. You can mention it, but you would need to say this one's the same age, so we know that these two correlate now. You have an unconformity here, you have one here. You don't really need one here. You should probably put one here, so you probably wouldn't even need that one, to tell you the truth, or even really this one. So that's just a quick summary of how absolute time can get a bit hairy, and how just because we absolutely date stuff doesn't mean we have lithostratigraphically correlated it, because you can't date things in the field. So you need to take that back to a lab, but we can get a better picture with these absolute dates. All right, so we can sit there and say too also that these basalts, even though they do not have the same age, these two, they are related. We know those are exactly the same age, and we can group these as well, and so forth and so forth. Okay, now I'm going to give you a real-world example of correlating rocks over distances. And remember how I talked in the GeoRant, how I said sometimes we're successful and sometimes we're not on assumptions? This is one of those times where some people are right, others are wrong. All right? This is an actual representation of a cross-section, except it's over It's over probably about 1,000 kilometers. We would say that this is the Keweenaw Fault, this is the Keweenaw Peninsula, this is the UP and into Wisconsin, and this will be the rest of the UP, the long part that's away from the Keweenaw. So essentially that way is north. Well, there was a big, and for a very, very long time, and I think I finally solved the problem last year after a couple years of field work, we had some dates, and since the 1990s we've been getting a lot better dates, and that is what allowed me to redefine what was called the Jacobsville Sandstone is now the Jacobsville Group. All right, PLV, Portage Lake Volcanics, CHF, Copper Harbor Formation, NS, None Such Shale, FS, Frida Sandstone, OS, Orientis Sandstone, DI, Devil's Island Sandstone, CS, Chickamauga Sandstone, and basically JS is Jacobsville Sandstone. Now, we have this massive fault here, all right? So what happened was, originally we had our law superpositions and we knew the relative ages of these rocks. And we have BG, which is the Bayfield group, which includes these three sandstones. Now, it was long suspected that those three sandstones might correlate with the Jacobsville over here. The Jacobsville does show some repetition, like the Bayfield group, the Orienta is an arkose, the DI is a quartz arenite, which is really rare for a terrestrial deposit in between two arkosic units. Chickamauga is also arkosic. All right, so the Jacobsville, that immature sequence was repeated in the Jacobsville. All right. Well, that's all nice and dandy, but that doesn't necessarily mean they correlate just because they're both sandstones. Well, it's a strong indication that they do, and it turns out they do. But our Portage Lake volcanics have been absolutely dated in the area at 1.094 billion years. These are all billions of years. Copper Harbor Formation, the red numbers are actual dated lava units. The green numbers are using other methods, which I'll touch on. The Copper Harbor Formation, although mostly a conglomerate sandstone, does have lava units in it, 1.086. The None Such, 1.081 using disseminated copper. The Frida has the Bear Lake stock intrusion in it, which is dated at 1.6 billion years, plus or minus 30. It's kind of, I wish somebody would redate that stuff. It was dated, I think, back in the 70s, maybe 60s. So margin of error is pretty big. And these dates are pulled from detrital zircons. Now remember, in sedimentary rocks, all these rocks will have zircons. But unlike igneous rocks, where the zircons form with the igneous rock and you can get an absolute date, in sedimentary rocks they do not. All zircons can tell you, if you pull out a zircon and you get 8 million years, say out of a sandstone, you pull a zircon out, you get 8 million years, that tells you that sandstone is 8 million years or younger. You can't be older than your oldest zircon. Okay, that's all it says. But in this case, it's enough to bracket it from the Precambrian, from the Cambrian-Precambrian line. And I think the oldest zircons are about 0.95, and clustered, I believe, around 1.2 billion. You're young, or wait, did I say that right? You can't be older than your youngest zircon. Sorry, you cannot be older than your youngest zircon. I should have wrote that down. So if your youngest zircon is 0.95, that tells you, oh, I didn't need to erase that, I didn't mean to, that formation at minimum started being deposited 950 million years ago, but likely later. And we pulled zircons from the Jacobsville as well, and we basically got the same thing at 0.95. All right, got the same trend, same peak and everything. So that told us that they were correlative. And my paper came out around the same time the zircon data for this stuff did. I was actually waiting for it, got impatient with the publish, but it came through right in time. So what I did was, since these units, even though they don't physically touch, and the closest they come is I think about 50 kilometers, we also got something else in the 90s. You see this here? It's called the St. Amour Core. It's over 4,000 feet of continuous 2-inch core or bigger. That is unheard of. And it's brilliant because it shows the relationship. It showed we had Frida below the Jacobsville, and I was able to pick out the unconformity in that core. The Frida sandstone is mostly narcotic sandstone and siltstone. And the reason why I have question mark after the Copper Harbor here is because it's a very quartz-rich conglomerate that's very thin that may or may not correlate with it. So once we had those dates, I could, and I did, correlate the Bayfield group with the Jacobsville group. And since Jacobsville, the name predates Bayfield, Jacobsville group, Jacobsville group. However, since we had no formal names within it on the Jacobsville, I pulled the Orienta over, I pulled the Devil's Island over, and I pulled the Checkamont over. Now there's two other units within the Jacobsville that are not present over here. One is the Jackson Creek, which is a fault proximal formation. That's only around the Keweenaw Fault within maybe 5 kilometers. It's not seen past that. And it pops up around other fault structures. And we have what I call the La'an Sandstone, which is likely upper top of Frida. But since there's no igneous intrusions in it, its type section is thin. It forms in paleo valleys on top of older igneous rocks. There's no way to date it, so I felt the need to actually give it a different unit. I wanted to put it within the Frida, but I just couldn't, there wasn't enough information to do that. All right, so this is how we tie absolute time into relative time to get a geologic sense of, to get a geologic history of the area. So what we know, so how we interpret that is our Portage Lake volcanics were deposited as mostly lava, rhyolite, andesite flows within the mid-continental rift as the continent tried to split apart and the area was now Lake Superior and extends past it under the surface. Once volcanism ceased, we started getting the Oronto group, the basal formation, which is this, the Copper Harbor formation. It's the basal formation of the Oronto group. Oh yeah, by the way, these are the Oronto group. And that has a couple lava flows in it, because even though technically the mid-continental rift had died, it was still having its death throes, if you will. So the Copper Harbor Formation contains igneous units. Then we know the Nonsuch Shale was deposited. We have an unconformity here. We have several smaller internal unconformities within the Copper Harbor. So it's mostly alluvial fan deposits. Then we have the Nonsuch, and then we had the Frida, okay, and they all are part of the Oronto group. The Frida's I'm tackling next year, but I'm going to leave the Nonsuch alone, I think. And over distances, these three intertongue with each other, but at the top there is a distinct unconformity, and one of the few places that unconformity is exposed is in the Saint Amour core, right here, all right? And we also know that Jacobsville has an angular and conformable relationship around pictured rocks with the above-lying Cambrian stone. So we know sandstones, we know that the Jacobsville is totally Precambrian, just late Precambrian, Neoproterozoic. And then we had our Jacobsville group deposited, our Orienta, Devil's Island, and our Chickamauga sandstone. And then the Keweenaw Fault is likely a long-lived fault. Obviously, it began being deposited, or it began showing signs of reversing, because it's a reverse fault, which may have initially been a normal fault that was reactivated reverse as the basin subsided and continental compression occurred as the Grenville front orogeny moved into Laurentia continent. So the Keweenaw Fault likely began its origins here, may even have continued up and through the Permian. That's still debated. We're still trying to figure that one out. But let's see, is there anything else I want to mention? A lot of early workers assumed the Jacobsville might actually be Cambrian in age, like lower Cambrian. And when we had only relative dating techniques, and actually Wisconsin Natural History Geological Survey people in the 60s and 70s, they left the Jacobsville question mark. Is it Cambrian or is it Precambrian? Well, now we know it is. And that was a big argument because the Oronto group is a mid-continent rift fill. as the basin subsided, it filled. It's clear as day that's what happened. You get the exact kind of sequence you'd expect to get in something like that. But the Jacobsville is a little different. It seems to have more of a south to north, or is it north to south deposition? I forget which way the crossbeds go. So it was borderline. It was terrestrial, but the Devil's Island was probably Aeolian windblown deposits. So it just seemed weird. So a lot of people, up until we started getting these dates, really didn't even know if it was Cambrian or Precambrian. But I think that's all I want to say about that. And that was a long segment. Apologize for there not being any cat appearances. I was really hoping there would be. But I just wanted to sit here real quick and summarize everything up. I went through with you on relative time, and then absolute dating techniques, absolute time, to show you how we correlate rocks. And then I gave you hypothetical examples, but I also gave you a real world example, which I think is important that a lot of professors might miss. It's important to get a degree in geology, at least out here. You have to attend what's called field camp, and it's a 6-week course. And if you don't get the chance to go on that, or your school doesn't have that kind of program, you should really think about doing it, because it really puts things into perspective for you and shows you how these things in the field relate to what you learn in a classroom. And people who don't understand geology or don't like it are usually people who have never looked at a rock outside of a classroom. And to understand these things, to sit there and go out and figure these things out for yourself, or like I did with the Jacobsville, it really shows you how old the Earth is and how complicated its systems are, which is something you don't get by sitting in a classroom studying books. That is important to establish a baseline, but it is not until you get out there. It's not really, you may have it in your head, but then you're just like, yeah, whatever. So I always invite, if someone has the time and they're local enough to me, I'm always welcome to bring somebody on a geologic excursion with me. Like I said, next spring and summer is going to be the field trip to redefine the Frida sandstone. I have a preconceptual model based on previous work of how I think it is organized, but I need to go out in the field and check this stuff. And I guarantee you I'm probably wrong, because the Frida is a very thick, very complex unit. It's on the order of 4,000 to 5,000 meters thick in places. So it's a very thick unit, and it's just been ignored because sandstones, like terrestrial sandstones like that, often are. But that's my plan, and I'm hoping the paper will be 2019 or maybe even 2020 by the time I get it out. But shameless book plugs before I go. This is my most recent book, Roadside Geology of the Algoma District, Ontario, from the Goulias River to Wawa to Potholes Provincial Nature Preserve. That's it right there. All right. This one is not that expensive. This one is not that long. It is only 70 pages. I forget how much it is. I think it's under $20 to purchase it. That is a roadside book. I have many roadside books, but there's like a sub-series within that, and Trans-Canada 17 is kind of one of that's the sub-series, and this is the second book in that series. The first one was done in 2007, and I did this for Canada's 150th anniversary. Happy birthday, Canada. But this one was the first one, and this is 2015. I think this one's around $20 to $23. I forget exactly. And this one is a little longer. It is 109 pages, and this one takes you through the Huronian supergroup, as where this one is mostly igneous rocks, metasedimentary rocks, highly metamorphosed rocks. They're both Precambrian books, and the goal is, I've already did the field work for this last year when we were up there, is to get, because this does Trans-Canada 17 and Ontario Route 638 up to the Goulias River. From there you go up Trans-Canada 17 and go east on Ontario 101, but it stops at Potholes. Well, what we did last year is we went from Potholes, actually we started south and went north, but from Potholes down 129 down to Trans-Canada 17. So that'll be the third sub-roadside book within my roadside book series. But anyway, I think that's it for today. I'm going to get my haircut Saturday. I know it's getting ridiculously long. But that's it. I hope you learned something.